We're in the Hall of Planet Earth, and I'm standing in front of one of my favorite samples from the Stillwater Complex in Montana, and it's one of my favorite samples because I've actually done research on this rock. What I want to do with it is to illustrate how we can date rocks by radiometric techniques. Now, geologists for more than 200 years have known the Earth is very old. They've made observations of relatively simple things such as unconformities, such as folded rocks, such as eroding mountains, and realized the Earth has to be not thousands of years, but millions of years old, and perhaps greater. But they never knew how old the Earth really was, or how long, basically, geologic processes require. But since the advent of radiometric dating, we've been able to answer those questions, and we've been able to determine precisely and quantitatively the ages of rocks. So now, in the case of the Stillwater complex, the Stillwater is a fossil magma chamber, if you will. It's a solidified magma chamber. It's solidified about 2.7 billion years ago, and it crops out right now in the Beartooth Range in southwestern Montana. So this rock is known as a gabbro. A gabbro is a rock that contains the white minerals plagioclase, green minerals, which are clinopyroxene, and brown minerals, which are orthopyroxene. Now the question is, how are we going to go about dating this rock? And I'm going to explain to you a method known as Samarium-Neodymium dating. Well, first of all, you have to prepare the rock. So we take a sample of this rock and we crush it up, and then we separate out the different minerals. So, and we've got them in vials right here. So this vial of white minerals, it's a vial of the plagioclase. The second vial is a vial of just the whole rock, the bulk rock, in other words, not separating the minerals. This next vial is the vial full of clinopyroxene. So again, these are very, very pure mineral separates. And this fourth vial is a vial of orthopyroxene. So we're going to analyze these four subsamples to determine age. So now I'd like to explain this method of dating using samarium and neodymium. And the things that you have to know about samarium and neodymium are, first of all, they're rare earths. They're one of a group of elements known as rare earth elements that are trace elements, but exist in almost everything. So they're rather common, and they're in concentrations that are easily measured by any number of techniques. The second thing you need to know is that samarium, the isotope samarium-147 is radioactive. Samarium-147 decays to neodymium-143 with a half-life of 1.06 times 10 to the 11 years, which is a lot of years, and I'm sure you can figure out how many billions of years that is. The other thing to realize is that there are a number of isotopes of neodymium. The stable isotope of neodymium is neodymium-144. There's one more thing that's really important to understand. When plagioclase, clinopyroxene, and orthopyroxene all crystallize from this liquid, they all start with the same ratio of neodymium-143 to neodymium-144. Okay, but they'll have different ratios of samarium-147 to neodymium-144, 143. So now what we can do is plot the two ratios that I just mentioned against each other. So here's a plot, the ratio of neodymium-143 divided by neodymium-144 against samarium-147 divided by neodymium-144. Now initially, the three different minerals, remember, they all started out life with the same neodymium-143 to 144 ratio, but they have different samarium to neodymium ratios. So they start out as a straight line here. So this is plagioclase, this is clinopyroxene, and this is orthopyroxene. So with time, the samarium decays away. This ratio, samarium-147 to neodymium-144, decreases, and the ratio of neodymium-143 to neodymium-144 increases. And again, the slope of that line is proportional to the age, and that allows us to calculate the age very precisely. Again, the age of this rock turns out to be approximately 2.7 billion years old, and we know it very precisely.